Look, I need you to forget something. Right now, before I say another word, I need you to reach into whatever mental filing cabinet you've been storing your understanding of quantum mechanics, and I need you to pull that folder out, set it on the desk in front of you, and recognize that most of what's in it, most of what you think you know, is either incomplete, misleading, or so philosophically neutered that it's become actively dangerous to real understanding. I'm not being dramatic. I spent the better part of 4 decades working inside this theory, arguing with the people who built it, and I'm telling you, the comfortable version of quantum mechanics that gets taught in textbooks, the version where you nod along and say, oh yes, particles are waves until you look at them, very strange, very mysterious, moving on. That version is not physics. That version is a ghost story dressed up in equations. And here's the thing that should bother you, the thing that should have been bothering you all along if anyone had been honest with you from the start. Quantum mechanics is the most precisely verified physical theory in the history of science. It has never been wrong, not once, not even slightly. Its predictions match experiment to 11 decimal places. And yet, and this is the part that physicists have been quietly sweeping under the rug for 100 years, nobody agrees on what it means. Nobody agrees on what is actually happening when a quantum system evolves, when it collapses, when measurement occurs, or what the word measurement even refers to. The most accurate theory we have is also the most philosophically unresolved theory we have. And for most of the 20th century, the response to that situation was, shut up and calculate. I was never good at shutting up. That's probably why I've had such an interesting career. So let's start from the beginning. Not from Schrödinger, not from Heisenberg, not even from Planck. Let's start from a question so simple it sounds stupid, and I promise you it is not stupid. The question is this: what is a physical system? You probably have an intuitive answer. A physical system is a thing, an electron, a baseball, a planet that exists in some definite state, and that state can, in principle, be known. The electron is here. The baseball is moving at this speed in this direction. The planet is at this position with this momentum. This is what we call classical intuition, and it served us beautifully for 3 centuries. Newton built a universe on it. Laplace famously said that a sufficiently powerful demon, an intelligence that knew the position and momentum of every particle in the universe, could, in principle, calculate the entire future and entire past of everything. Determinism, completeness. The universe is a clockwork machine that, given enough information, yields no surprises. Quantum mechanics didn't just poke a hole in that picture. It took the picture out back and shot it. Here is what quantum mechanics actually says, stated as plainly as I know how to state it. A physical system does not, in general, have a definite value for its observable properties prior to measurement. Not we don't know the value, not the value is there but hidden. The value in the most honest mathematical language we have for describing nature does not exist until the act of measurement brings it into existence. The electron does not have a definite position. It has a wave function, a mathematical object that assigns probability amplitudes to every possible position simultaneously. When you measure the position, you get one answer. But before the measurement, the question, where is the electron, does not have an answer. Not because we're ignorant, because there is no answer to be ignorant of. Now, I know what you're thinking. You're thinking, that's insane. Things have to exist somewhere. Reality has to be real. And I have enormous sympathy for that reaction because I had it myself. I had it for years. When I was a graduate student, I thought the people telling me this were being unnecessarily mystical, that there had to be some deeper layer of description where the electron really does have a position, we just can't access it. Hidden variables. The universe is a machine we can't quite read, rather than a machine that genuinely doesn't have the hidden states we're looking for. That intuition is wrong. And I can tell you exactly when I realized it was wrong. It was 1964, and a man named John Bell did something that should have made every physicist in the world stop dead in their tracks. Bell proved a theorem, a mathematical theorem, not a philosophical opinion that put the hidden variable hypothesis on trial. He showed that if you believe quantum systems have definite hidden properties prior to measurement, then certain statistical correlations between distant measurements must obey an inequality, a hard mathematical bound. And then experiments starting with Clauser and Friedman in 1972, perfected by Alan Aspect in 1982, and driven to absolute precision by Zeilinger and colleagues in more recent decades, Those experiments showed that nature violates Bell's inequality cleanly, unambiguously, repeatedly. So the universe is not hiding information from us. There is no hidden layer where everything is definite and classical and comforting. The indeterminacy is not in our heads, it is in the world. Now, here is where it gets strange. And I mean genuinely strange, not, oh, how whimsical particles are waves strange, but stay up at 3 in the morning questioning the nature of reality strange. The Bell experiment doesn't just tell us that hidden variables don't work. It tells us something about the structure of space itself. Because the Bell correlations, the correlations that violate the inequality, they appear between particles that can be arbitrarily far apart. You can separate two entangled particles by a kilometer, by a light year, and when you measure one, the measurement results will be correlated with the measurement of the other in ways that no local hidden variable theory can account for. The correlations are non-local. They seem to reach across space instantaneously. And this is absolutely crucial, so stay with me. You cannot use these correlations to send information. This is not a loophole in the weirdness. This is not nature being sneaky. It is a deep feature of the theory. The non-locality of quantum mechanics is real, and it is non-signaling. You cannot use entanglement to send a message faster than light. And that means Einstein's relativity is not violated, at least not in the causal sense. But it also means that our notion of space, the idea that things separated by space are fundamentally independent, that what happens here is in principle separable from what happens there, is wrong. Quantum mechanics is telling us that the universe is, in some deep sense, not made of locally independent pieces. It is telling us that separability itself, the assumption that distant things are genuinely separate things, is a classical prejudice that nature does not share. I want to sit with that for a moment because I don't think it's appreciated enough. We tend to think of entanglement as a strange property of particles, a quantum weirdness that applies to the very small and fades away as things get large and classical. But entanglement is not a quirk. Entanglement is the generic condition of quantum systems. Unentangled states are the special case. When two quantum systems interact, they become entangled, and in principle, that entanglement never goes away. It spreads, it dilutes, it gets harder to detect, but it doesn't disappear. The universe we live in, if quantum mechanics is correct all the way up, and there is no evidence that it isn't, is a universe in which everything that has ever interacted is, in some technical sense, entangled with everything it has interacted with. The entire observable universe may be, at the level of its quantum state, one gigantic entangled system. What we call separate objects may be better described as separate features of a single quantum state that only look separate to us because of the particular coarse-grained way we have access to it. That is not philosophy, that is physics. That is what the formalism says. Now, I promised you quantum physics reborn. And I want to be precise about what I mean because the word reborn can be abused. I'm not telling you that quantum mechanics is being replaced. I'm telling you that the last 15 years have produced a shift in how we understand what quantum mechanics is about, a shift so fundamental that it changes the questions we think we should be asking. And that shift comes from a direction most people wouldn't expect. It comes from information theory. Here's the setup. For most of the 20th century, quantum mechanics was understood as a theory about physical systems, about electrons and photons and atoms and what they do. The wave function was a description of a system. Measurement was a physical process. The Schrödinger equation told you how the state evolved in time. This is all true and it all works. But it frames the question as, what are the systems? What are their states? What are the dynamics? Starting in the 1990s, a different framing began to emerge. What if quantum mechanics is not primarily a theory about systems, but a theory about information, about what can be known, by whom, under what circumstances, and how knowledge propagates? What if the right question is not, what is the electron doing, but what constraints does nature place on the acquisition and communication of information about physical systems? This reframing sounds like it could be pure philosophy. It is not. It is producing real mathematics, real theorems, real experimental predictions, and it is dissolving problems that seemed intractable under the old framing. Let me give you a concrete example, and I want to walk through it carefully because I think it's the most important conceptual development in the foundations of physics in the last half century. The problem is called the black hole information paradox, and I have a personal history with it that I'll get to in a moment. Here's the setup. According to general relativity, a black hole is a region of space-time from which nothing, not matter, not light, not any kind of signal can escape to the outside universe. The boundary of that region is the event horizon. Anything that crosses the horizon is gone, causally severed from the outside universe. Information about whatever fell in is, from the outside's perspective, lost. Now, in 1974, Stephen Hawking showed something extraordinary. Black holes are not completely black. Quantum field theory and curved spacetime, which is quantum mechanics applied to the vicinity of a black hole's horizon, predicts that black holes emit radiation, thermal radiation. A black hole behaves to a remarkable approximation like a glowing hot object with a temperature inversely proportional to its mass. This is called Hawking radiation, and it means that black holes evaporate slowly over enormous timescales, but they evaporate, they lose mass, they shrink, and eventually, in the theory, they disappear. Here's the problem. The Hawking radiation is thermal. It is, as far as the calculation shows, perfectly random. It carries no information about what fell into the black hole. If you throw an encyclopedia into a black hole and wait for it to evaporate via Hawking radiation, what comes out is thermal noise. The information in the encyclopedia, the specific arrangement of its atoms, the correlations that made it a book and not a pile of random matter, that information is gone, destroyed, not hidden, not scrambled beyond retrieval, gone. But quantum mechanics is a unitary theory. Unitarity is the technical term for the property that quantum evolution preserves information. Given the final state of a quantum system, unitarity guarantees that you can reconstruct the initial state. If unitarity is right, and quantum mechanics is a universal theory, true all the way up, true even in the presence of black holes, then information cannot be destroyed. Not ever. Not even by black holes. Hawking said, information is destroyed. Unitarity breaks down your black holes. I said, no. And so did a lot of other people, and this became one of the genuinely great arguments in the history of theoretical physics. The resolution, and this is where it gets beautiful, in the specific way that things are beautiful when the universe turns out to be more ingeniously organized than you had any right to expect, the resolution came not from a correction to Hawking's calculation, but from a fundamental re-understanding of what space and quantum information have to do with each other. The key insight is this. The Hawking radiation that comes out of a black hole is not independent. It is entangled. Each early Hawking photon is entangled with later Hawking photons, and through this web of entanglement, information about the infalling matter is gradually encoded in the outgoing radiation, not in any single photon, not in any local feature of the radiation, but in the long-range correlations, the entanglement structure of the entire Hawking radiation field. The information is not lost. It is hidden in the correlations, and recovering it would require a measurement of extraordinary complexity, exponentially difficult, practically impossible, but in principle present. This argument, developed through the work of Don Page, later made quantitative and rigorous through the development of quantum error correction and holographic entropy bounds, requires a picture of the black hole that would have been unthinkable 30 years ago. The interior of the black hole, the degrees of freedom behind the horizon, must be in some sense encoded in the exterior. The information that describes what's inside the horizon must be recoverable from what's outside the horizon. The black hole's interior is not a separate region of space-time with private information. It is, in the language of quantum information, entangled with the exterior in a way that preserves the total information content. And this brings me to the holographic principle, which is, in my honest opinion, the most audacious true thing that has ever been said about the structure of physical reality. The holographic principle, developed in the early 1990s by Gerard Hooft and then significantly extended by my own work, and I want to be honest about this because it's important. This was not received wisdom, and this was a fight. The holographic principle says that the information content of any region of space is not proportional to the volume of that region. It is proportional to the area of its boundary. A region of space bounded by a surface of area A contains at most A 4 times the Planck area bits of information, not more. The three-dimensional volume is in some fundamental sense redundant. All the physics happening inside a volume is fully encoded on the two-dimensional surface surrounding it. I know how that sounds. It sounds like a metaphor. It is not a metaphor. It is a mathematical result that follows from combining quantum mechanics with general relativity, and it is confirmed in its most precise form by the ADS-CFT correspondence, which is a concrete, explicit duality between a gravitational theory in a space and a non-gravitational quantum field theory on its boundary. Juan Maldacena discovered this duality in 1997, and it is probably the single most important theoretical result in physics since the formulation of quantum mechanics itself. It is not a conjecture in the hand-wavy sense. It has been verified in thousands of calculations. The gravitational theory and the boundary theory agree in every case where both can be computed to arbitrary precision. What does ADS-CFT mean? It means gravity is not fundamental. Space-time is not fundamental. What you think of as the three-dimensional geometry of space, the metric, the curvature, Einstein's equations, all of that is emergent. It is a derived description that emerges in some appropriate limit from a quantum system that lives on the boundary and knows nothing about bulk geometry. Space is not the stage on which physics happens. Space is a consequence of quantum information of entanglement patterns in a boundary theory projected inward. Now here is where it gets strange. No, I already said that. Here is where it gets unsettling. I have been working on physics for 50 years. I have been thinking about the relationship between quantum mechanics and space-time for most of that time. I fought for the holographic principle when it was considered fringe. I watched it become mainstream. And I am telling you now, honestly and without any attempt to be reassuring, I do not know what it means that space-time is emergent. None of us know. We have the duality, we have the mathematics, we can do calculations. But the question, what is space-time made of in a deep sense, that question does not yet have an answer. There is a partial answer. The partial answer comes from work done in the last decade connecting entanglement directly to geometry. Mark van Ramsdonk wrote a beautiful paper in 2010, more beautiful than it was initially recognized, to be arguing that entanglement in the boundary quantum theory is directly related to geometric connectivity in the bulk. If you take two separate boundary theories that are not entangled, the corresponding bulk geometries are disconnected, two separate spacetimes with no geometric bridge between them. If you entangle those boundary theories, a geometric connection, a wormhole forms in the bulk. The geometry of spacetime, its connectivity, its very topology, is dual to the entanglement structure of the boundary quantum state. Juan Maldacena and Leonard Susskind, which is to say, people working very hard on this right now have made this precise with the ER equals EPR conjecture. ER is Einstein-Rosen, a wormhole. EPR is Einstein-Podolsky-Rosen, quantum entanglement. The conjecture says these are the same thing. An Einstein-Rosen bridge connecting two regions of spacetime is equivalent to quantum entanglement between the degrees of freedom in those regions. The geometric connectivity of space and the quantum informational connectivity of entanglement are not analogous. They are identical. If that's true, and I believe it is not on faith, but because the mathematical evidence is consistent and substantial, then space-time literally is made of entanglement. The geometry we perceive, the distance between objects, the curvature that causes gravity, all of it is a macroscopic emergent phenomenon that arises when you have many quantum degrees of freedom structured by entanglement in particular ways. Take away the entanglement and the space falls apart. Literally, the geometric connection disappears. I want to give you a concrete way to think about this. Imagine a sheet of paper, it has points on it. Those points are connected nearby, points are nearby, distant points are distant. The geometry of the sheet is what relates points to each other. Now, imagine the sheet is not fundamental. Imagine that what's real is a collection of abstract objects, qubits, if you like, and what defines the geometry of the sheet is the pattern of entanglement among those qubits. Two qubits that are strongly entangled are nearby in the emergent geometry. Two qubits with little entanglement are far apart. The sheet itself, the spatial geometry, is a derived object. It's what you see when you look at the entanglement structure from the right angle. Now cut the entanglement between two regions. What happens to the sheet? The two sides become disconnected. They become separate spaces. You've torn space-time not by any mechanical action on the geometry, but by reducing quantum correlations between the degrees of freedom that constitute it. This is not science fiction. This is where the actual research is. This is what people are computing, testing against AD-CFT, and trying to make precise enough to extend beyond the special case of anti-de Sitter space into the universe we actually live in. And here I want to say something about the quantum mechanics that most of you learned, the version that sits in your textbook between the chapters on classical waves and solid-state physics. That version has the wave function, the Schrödinger equation, the postulates of measurement, Born's rule, you know the drill. That version is correct as a computational tool. It will give you the right answer every time. But it is incomplete as a conceptual framework, and the incompleteness is not a detail, it is the central problem. The measurement problem. Let me be direct about this because it deserves directness. Quantum mechanics has two rules for how systems evolve. Rule 1. Between measurements, a quantum system evolves according to the Schrödinger equation, which is deterministic, linear, and unitary. It preserves information. It never collapses anything. It just rotates the wave function in Hilbert space. Rule 2. When a measurement occurs, the wave function collapses discontinuously, non-linearly, non-unitarily to one of the possible outcomes, with probabilities given by Born's rule. These two rules are in apparent contradiction with each other, and the question of when Rule 2 applies, which physical processes count as measurements, what exactly constitutes a measurement in the physical universe, that question has no agreed answer. It is the deepest unresolved problem in the foundations of physics, and it has been unresolved for 90 years. I want to be precise about why the usual answers don't work. The Copenhagen interpretation says, don't ask what's really happening, just apply the rules correctly and the rules work. This is true. The rules work, but don't ask what's really happening is not a physical theory. It's a prohibition. It tells physicists to not do physics. I've never been comfortable with prohibitions masquerading as answers. Decoherence, the idea that quantum coherence is suppressed by interaction with the environment, is real and important. It explains why we don't see macroscopic superpositions. It explains why a measuring apparatus quickly becomes correlated with one outcome rather than remaining in a superposition. But decoherence doesn't collapse the wave function. Mathematically, decoherence produces a density matrix that looks diagonal, that looks like it's already collapsed, but the full quantum state, including the environment, is still a superposition. Decoherence explains why the cat looks either dead or alive. It doesn't explain why the cat is dead or alive, rather than some superposition that we simply can't detect. That's not the same thing. The many worlds interpretation says Rule 2 never happens, the wave function never collapses, all outcomes occur. After a measurement, the universe splits into branches, one for each outcome, and you end up in one branch. The math is clean. Unitarity is preserved. Everything is consistent. But we haven't derived Born's rule from this picture in a way that fully satisfies explaining why you should expect outcomes with the quantum mechanical probabilities rather than treating all branches as equally real. And the interpretation has the small matter of positing an essentially infinite number of unobservable universes every time a quantum event occurs. That may be right, I'm not dismissing it. But it hasn't yet fully earned its keep. I don't know which interpretation is right, and neither does anyone else. And I find that fact, the fact that we have a theory of extraordinary precision that we cannot agree on how to interpret, not depressing but genuinely exciting. It means there is still a conceptual revolution to be had. We are not at the end of this road. Now, let me bring this back to something concrete and recent, because I promised you Quantum Physics Reborn, and I've been delivering Quantum Physics Foundationally Troubled, which is related but not the same thing. The rebirth I'm pointing at is the recognition, gradual, hard-fought, still incomplete, that quantum mechanics is not just a theory about particles. It is a theory about information, and information is the right language for understanding not just quantum systems in isolation, but quantum systems in interaction with each other, with measuring devices, with space-time, and with gravity. The conceptual tools of quantum information entanglement entropy, quantum error correction, quantum channels, The algebra of quantum operations, these are not just practical tools for building quantum computers. They are turning out to be the right language for the deep structure of physics. Let me give you an example that I think crystallizes this. Consider the entropy of a black hole. Bekenstein showed in 1972 that a black hole's entropy is proportional to its horizon area. Hawking confirmed this with his temperature calculation. The Bekenstein-Hawking entropy formula is S equals A over 4 inches Planck units, where A is the area of the horizon. This formula was mysterious for 20 years. Entropy usually counts microstates, the number of different microscopic configurations of a system that give the same macroscopic appearance. What are the microstates of a black hole? What is it counting? The answer that quantum gravity and ADS CFT provide: the black hole entropy counts the entanglement entropy of the degrees of freedom behind the horizon with the degrees of freedom outside it. The horizon area is a measure of quantum entanglement across the boundary. Bekenstein's formula, reinterpreted, says that the amount of information you cannot access when you're outside the horizon, the information hidden behind it, is proportional to the area of the horizon. And there's a maximum: you cannot hide more than 4 bits behind any surface of area A. This is the covariant entropy bound, and it is one of the deepest results in all of physics. What does it mean? It means that in a gravitational theory, entanglement and geometry are not independent. The area of a surface, a geometric quantity, is also an entanglement entropy, a quantum information quantity. Geometry is quantified by quantum information. The curvature of space-time is in some sense a measure of how the quantum information in the system is organized. The Ryu-Takayanagi formula, discovered in 2006, makes this precise in ADS CFT. The entanglement entropy of a region in the boundary quantum theory is equal to the area of a minimal surface in the bulk in Planck units. This is the holographic encoding made quantitative. Entanglement in the boundary corresponds to geometry in the bulk. And this formula has been the engine of an enormous amount of progress, understanding how the bulk reconstructs boundary information, understanding quantum error correction in ADS, CFT, understanding how the interior of a black hole is encoded in the exterior radiation. This is the rebirth I'm talking about. Quantum mechanics reborn not as a theory about the wave function of particles, but as a theory about the architecture of information. And that architecture is, at the deepest level, the architecture of space-time itself. Now, I want to say something that I think is important and that I don't always say, because it sounds like it might undermine the confidence that physics deserves. All of this ADS divided by CFT, holography, ER equals EPR, the emergence of space-time from entanglement, all of it is worked out in a specific setting. Anti-de Sitter space, a space with a negative cosmological constant, a space that is not the universe we actually live in. We live in a universe with a positive cosmological constant, an expanding universe, a de Sitter-like universe. And the holographic duality for de Sitter space, the theory of quantum gravity in the universe we actually inhabit, is not known. I have spent a significant portion of the last decade thinking about this. I believe the answer is there. I believe that there is a holographic description of our universe, that the physics of our cosmos is encoded on some surface, that entanglement and geometry are unified in our space-time just as they are in ADS CFT. But I cannot prove it, and neither can anyone else. The tools that work so beautifully in the anti-de Sitter case rely on the presence of a conformal boundary, a place at infinity where the boundary theory lives. And our universe does not have such a boundary in the same technical sense. There are proposals, there is progress, but the problem is open. And let me tell you something about open problems. Open problems in physics are not admissions of failure. They are the sign that a field is alive. A physics that has no open questions is a physics that has become a museum piece, a collection of solved puzzles to be shown to tourists. The fact that we cannot yet write the holographic theory of our universe tells me that we are in the middle of something enormous. We are somewhere inside a revolution whose end we cannot see, working by the light of the partial understanding we have managed to accumulate. I think about Niels Bohr and Werner Heisenberg in 1925, 1926, working out the formalism of quantum mechanics. They knew they had something extraordinary. They knew the formalism worked. But they did not know, could not have known, that their theory would eventually be understood as a theory about information, that it would illuminate the nature of space-time, that it would provide the conceptual framework for understanding the origin of geometry itself. The theory was right before anyone understood what it was right about. I suspect we are in a similar situation now. We have the mathematical structures. We are still learning what they mean. Now let me talk about experiment. Because I'm a physicist, not a philosopher, and the question, how do we test any of this, is the right question, and you should be asking it. Some of it is already tested. Bell's theorem violations are experimental fact. Entanglement is experimentally established beyond any reasonable doubt. Quantum error correction works. It's the basis of the quantum computing architectures being built right now. The thermodynamics of black holes, derived from holographic principles, gives results consistent with known physics wherever they can be independently checked. The deeper claims about the emergence of space-time, about the interior of black holes, about quantum gravity and de Sitter space, those require either observations we cannot yet make, or mathematical consistency arguments, or the internal coherence of a framework that is not yet complete. This is the state of fundamental physics at the frontier. It is honest to say so. There is one experimental frontier that I find genuinely electrifying: quantum gravity effects at the horizon scale. The firewall paradox proposed by Almheri, Marolf, Polchinski, and Sully in 2012, the AMPS paper argues that if information is preserved, the interior of a black hole, as described by classical general relativity, cannot exist. An infalling observer, according to AMPS, does not pass through the horizon smoothly into an ordinary interior region. Instead, they encounter a firewall, a wall of high-energy radiation at the horizon, generated by the quantum state that preserves information. The classical picture of a black hole interior, where a freely falling observer notices nothing special at the horizon, is wrong. I don't know if AMPS is right. The debate is unresolved. The debate involves some of the best physicists alive. If AMPS is right, it means that the classical general relativistic description of black hole interiors breaks down at the horizon, not just near the singularity. It means that quantum effects are not confined to extreme conditions, but show up at the very horizon of a macroscopic black hole. It means the geometry of space-time itself is modified by quantum information constraints. This is not a question we can currently answer experimentally. Black holes are not laboratory objects. But it is a question we can study theoretically, and the attempt to answer it has already generated enormous progress in understanding entanglement, entropy, and the structure of quantum gravity. I want to close with something that I've been thinking about for a long time, something that connects the technical content we've been discussing to a question that I think is the deepest question in physics, possibly the deepest question available to human thought. Why does quantum mechanics work? Not how do we use it? Why does the universe obey its rules? Why is the fundamental description of nature probabilistic? Why does entanglement exist? Why are there non-local correlations that are nonetheless non-signaling? Why is unitarity true? Why is information conserved? These questions don't have answers in the current framework. Quantum mechanics does not explain itself. It gives us rules and the rules work, but the question of why these rules and not others, why this particular framework for describing the relationship between physical systems and information, that question points outside the theory. It points to whatever is more fundamental than quantum mechanics. Here is the possibility that keeps me up at night. The possibility that I think is serious, that I think the evidence is beginning to support, that I have argued for and against and come back to more times than I can count. What if quantum mechanics is not the final framework? What if quantum mechanics is itself emergent, not the bedrock of reality, but a derived description that emerges from something even more fundamental? What if the rules of quantum mechanics, superposition, entanglement, Born's rule, unitarity are not axioms of nature, but theorems derived from deeper principles that we haven't yet identified? There are hints. The information theoretic reconstructions of quantum theory, the work of Cirabella, Dariano, Perinotti, and others show that quantum mechanics can be derived from a small set of purely operational principles about what kinds of experiments can be done and how results can be combined. Quantum mechanics is not the only possible probabilistic theory. Classical probability theory is another. But quantum mechanics occupies a special place in the space of possible theories, and it occupies that place for mathematical reasons reasons related to the structure of information and the constraints on what can be known. This suggests that quantum mechanics is selected, not arbitrary. The universe is not quantum mechanical by accident. There is something about the structure of information itself that forces quantum mechanics to be the right framework. If that's true, if quantum mechanics is derived from information theoretic principles, then the question of why quantum mechanics becomes the question of why these information theoretic principles. And that question, I suspect, has an answer that is connected to space-time, connected to the emergence of geometry from entanglement, connected to the holographic principle. The reason quantum mechanics is the right framework for physics may be that quantum mechanics is precisely the framework that is consistent with space-time being emergent from information, and the universe we live in is one in which space-time is emergent from information. That would mean that the laws of physics are not written into the universe from outside. They are consequences of the structure of quantum information, and the structure of quantum information is at the deepest level what the universe is made of, not particles, not fields, not geometry. Information, quantum information, organized according to the patterns we see reflected in entanglement, entropy, and holographic bounds, and the strange non-local correlations that Bell showed us 60 years ago, we should be paying attention to. I don't know if this is right. I think it might be right. I think the evidence is suggestive and the mathematical coherence is encouraging, and the fact that every time someone has followed this thread seriously, they have found it connected to something real. That pattern is not nothing. But here is what I know. I know that quantum mechanics has been telling us something for 90 years that we have not fully heard. We have been so busy using it, building lasers, transistors, MRI machines, computers, that we have not sat with it long enough to understand what it is actually saying. What it is saying is not particles are weird. What it is saying is information is fundamental. Entanglement is not a property of particles, it is the fabric of the world. Geometry is not the stage on which physics happens, it is a consequence of how information is arranged. The universe is not a collection of things. It is a structure of relationships, of correlations, of quantum information organized in ways we are only beginning to understand. The quantum physics that is being reborn right now is not a corrected version of the old quantum physics. It is quantum physics grown up. It is quantum physics that has stopped apologizing for being weird and started asking what the weirdness is trying to tell us. It is quantum physics that has picked up the tools of information theory and looked at space-time with them and discovered that space-time is not what we thought, that it is softer, more structured, more information-like than the classical picture ever suggested. And the question you should be sitting with, the question I have been sitting with for most of my life and that I have not finished sitting with, is this. If space-time is made of entanglement, and if quantum mechanics is the theory of entanglement, and if quantum mechanics itself turns out to be derivable from deeper principles, then what are those deeper principles? What is the thing that the universe fundamentally is before it puts on the costume of space and time and particles and fields? What is the universe in itself underneath the layers of emergent description? I don't have the answer. Nobody does. But I want you to notice that we now have the tools to ask the question precisely. We have the mathematics, we have the duality, we have the entanglement structure. We have the beginnings of a framework in which the question is not just philosophical but technical, where what is space-time made of has a mathematical answer and experiments, even if distant and difficult, that could in principle test it. That is not a small thing. That is everything. That is what physics is for. Don't let anyone tell you the revolution is over. Don't let anyone tell you the foundations are settled. The foundations have never been less settled. In the best possible way, unsettled, the way a good argument is unsettled, the way a problem is unsettled when you finally understood what the problem actually is. Go argue about it. I'll be in the back doing the same.